Okay, folks, here we are in section 3.14, talking about the very useful topic of regularized least squares. So this is regularization is going to allow us to exert some control over the weights that we learn when we're doing least squares regression. So let's get into it. Okay, so yeah, back in 1.1, remember we were fitting these polynomials and we had these high order polynomials and they were giving us really like wobbly solutions that we suspected weren't going to be robust. So one solution we had there was to regularize the weights, because we looked at the weights and we saw that some of those solutions had like gigantic weights that seemed to be fitted just to the pattern of noise that we had. So we decided, hey, well, let's put in some penalties on large weights to avoid solutions like that and hopefully find more robust solutions. And so that's what we did there, and that's kind of what we're talking about here. And we also saw there that regularization can also have a probabilistic interpretation as kind of a prior on the weights. We're not going to talk about that connection here, but it's just something to keep in the back of your mind. Okay, so let's get into it. So we introduced the idea of adding a regularization term to an error function in order to control overfitting. So the total error function to be minimized takes the form of, this is I guess from the data, and then there's some measure of the weight, so the E of W, we'll see what that looks like in a sec. There's an example with some penalization parameter. And gamma is the regularization coefficient that controls the relative importance of the data-dependent error and the regularization term EW. So as we send lambda to infinity, this regularization term is going to become more important. Setting it to 0 is going to make the data more important. So it'll make it, setting it to 0 will make the data be the only thing that matters. So it'll be like you're not doing any regularization. I haven't seen things where they use negative regularization. I guess would that even favor the data more? I'm not sure. But yeah, so all I've seen is lambda 0 to positive. Okay. Now, one of the simplest forms of regularizer is given by the sum of squares of the weight vector elements. So let's highlight this guy. This is really simple and also very easy to analyze. So always a good one to start with. And so what are we doing here with it? What is this? If you're still not comfortable with the vector notation, which you should be getting comfortable with by now, so do make sure you do practice that, because it's really, really useful. But it's going to be equal to 1/2 on sum on Wi transpose. So, whatever the dimensionality of your data. So you're just summing, you're penalizing the sum of the squared weights. Or you can think of it as kind of the squared length of the weights. If we also consider the sum of squares error function given by this, which you've seen already in the previous section, then the total error function becomes, well, this plus the regularization. Okay, so this particular choice of regularizer is known in the machine learning literature as weight decay, because in sequential learning algorithms, it encourages weight values to decay towards 0 unless supported by the data. So remember, so what he's saying here is, you'll remember, we're going to call this our, let's just call it, I don't know, our L of W. And remember how it worked in sequential learning. So you would go, WT plus 1 is equal to WT minus times the gradient of L, something like that, right? Well, if we compute the gradient of L up there, is going to equal to what? It's going to be, let's say, it's going to be the sum on n equal to 1 to n times t of n minus Wt phi, I'll just call it phi n, plus lambda times w, right? So if we kind of plug this, if we plug this into here, what we'll get is that this is actually equal to Wt minus eta times, lambda times Wt, it should be plus this sum on n terms. And that doesn't really matter. So this is just going to be some term that's going to be pushing you with the data, but this is going to be some additional pressure downwards on the weights. And so you can see that if this term wasn't here, then these weights would actually eventually be pulled towards 0, because you're getting, you're getting some kind of additional, there's kind of an additional force here pushing the weights down. So that's kind of why it's called weight decay. It actually causes, on its own would cause the weights to decay to zero. In the presence of data, well, the weights, you do learn some weights that are related to the data, but they will tend to be smaller than they would normally be without that term present. Okay, so let's keep going. Now it says it has the advantage, right? So it provides an example of a parameter shrinkage method because it shrinks parameter values towards zero. Okay, we'll see how that works in a second. And the important thing is it shrinks them towards zero, but it will almost never shrink them to exactly zero. And that's going to be important later on when we talk about kind of sparsity inducing methods, which actually can shrink the weights to exactly zero. So you don't have to, like with those methods, you don't have to, like, for example, put in a threshold that says, okay, weights below a certain level, I'm just going to treat as zero. It will actually force weights to like actual zero. And we'll see geometrically also why that happens. Whereas with weight decay or shrinkage, the weights kind of get scaled down, but they will never be, if it was kind of non-zero in the, let's say, in the unregularized case, they'll never, I don't want to say never, but I actually think it is never for this kind of regularization, for the least squares regularization. They'll never get shrunk down to exactly zero. So we'll see how that works in a second. So it has the advantage that the error function remains a quadratic function of W, and so its exact minimizer can be found in closed form. So if we just kind of plug all that stuff in and solve for W, you should do this. We obtain this expression. So remember, we used to, our old expression for W didn't have this in it. It was just phi t phi minus 1 times phi t, and now we've got this lambda term showing up. And this represents a simple extension of the least squares solution. Okay, so now the question is, now we can actually use SVD, singular value decomposition, to actually see kind of what the shrinkage is all about. So let's do that. Okay, so let me make sure you guys can see. Okay, so suppose that phi looks like that. Okay, so it has kind of an SVD that looks like this. Then phi t phi is going to be what? It's going to be s squared v transpose. Okay, so now we can write this weight is going to be, and also keep in mind that I can be written as v transpose. Good. So we can write this as v transpose plus to the minus 1 times phi of t. Okay, I don't think I need to expand that last one yet, so let's not do that just yet. And I'll zoom in a bit so we have a bit more room. Okay, so now what we can do is we can actually just extract the v and put it on the outside. So it's actually equal to v times lambda I plus s squared v transpose to the minus 1 times phi t t. And so then what will happen was that this is going to equal to the minus 1 actually comes and works on the diagonal, so it's going to be v times lambda I plus s squared to the minus 1 times v transpose times phi t t. Okay, that's great. Okay, so now let's just look at, so this is what our weights are going to be. What do I want to say here? Yeah. Okay. So let's just. So this is fine. So now we say, okay, well, let's just expand everything. So now we've got v times lambda I plus s squared to the minus 1 times v transpose times v times s times u transpose times t. Okay, and so this will cancel out, and you end up getting, this is v times s over lambda I plus s squared times u transpose times t. Okay, so that's going to be our weights. And now to actually see that, you can kind of already see the shrinkage happening because you can see there's a lambda plus s squared that's kind of scaling everything. But what we'll do is, it's slightly easier to see it if we just change to these w coordinates. So we'll multiply both sides by v transpose, and we'll just call these w tildes, v transpose w, and it's going to equal to s over lambda I plus s squared times u transpose t. So you can see that kind of compared to the case where there's no regularization, where the w tildes would just be s over s squared u transpose t, we're now actually kind of shrinking them down a bit more. So the larger lambda is, the more things are going to get compressed. And then we can kind of look at what this function looks like. And if we actually kind of plot it out, we'll see that, let's say this is s, and then we'll just call this s prime. Or let's call it actually s lambda. Okay, so what's coming out on this end is going to be, we're going to call it s lambda. And we can see that for large values of s, well, this whole thing is going to behave like 1 over s. So it's not, the lambda is not going to matter. So we're going to have like, let me do a different color. So, if we didn't have the regularization term there, we're just going to look like this. And notice that as s is getting, for very small values of s, we would actually get very large weights. So now what the role of this regularization term is that, if you look at it again, what happens for very small values of s? So if s squared is much less than lambda, then this bottom term kind of just behaves like lambda. So you get kind of linear behavior going towards 0 with some slope of kind of 1 over lambda. And so when you combine these two pieces of behavior, you get kind of let me change colors, you get this net effect that kind of looks like this. And this point is going to be, I believe it's like at root lambda. And this height is like 1 over root lambda, something like that. But effectively what it does is it's kind of shrinking. So if your weights are very large, nothing happens to them. But if they're kind of, if your weights are very small, greater than, I guess on that scale, then if they're very large, then if they're very small, they kind of keep their, they keep their value, just like here, right? So when s is very large, the net effect of this is 1 over of the s squared dominates the lambda, and the net effect is nothing, based almost as if lambda is not there. But if s is very small, then normally the weight would actually end up being very large because the weight is proportional to kind of 1 over s. But because of this regularization term here, it kind of gets shrunk back down. So you end up kind of controlling it, you end up controlling how big your weights get. So that's kind of the intuition for kind of where these terms come from, how the thing actually works. And the key, as very frequently, is kind of SVD to kind of show you what's going on. So hopefully that gives you kind of a sense of where shrinkage comes from. Okay, so now this is good. Okay. Let me erase some of this stuff so we can see a little bit more easily. Okay. A more general regularizer is sometimes used, for which the regularized error takes the form, this is our normal error function, plus, now we're regularizing something, but there's kind of a Q term here. So let's highlight that. There's a Q. So Q equals 2 is what we just dealt with, the quadratic regularizer. And figure 3.3 shows contour as a regularization function. Okay, so I always used to see these and I'd be like, well, that's kind of cool, but like, so what? Like, what is it? How does it determine what solutions we're going to learn? There's a nice image on the next page we're going to discuss, which will kind of give you some intuition for why these various shapes, matter. And so these are contours. So these are the sets that, like, sum w to the q is equal to 1, let's say. And notice that one of the key distinctions between all these shapes is that all of these guys, so this is convex, 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 not convex. And so convex means that if you have kind of any 2 points that are inside, then all the points in between are also inside your little circle here. or your little, you know. And this can mean, if you combine it with the convex loss, an appropriately behaving loss, like the squared loss, then your whole function will have this nice property that it's convex, and it will not have any local minima, and lots of nice things like that. But a function like this, you know, when q becomes less than 1, then it stops becoming convex. So for example here, I have a point here and I have a point there, but if I you can see that I can kind of go across and leave that set. So, you know, when things get very pointy, they lose convexity, and then all of a sudden it's possible to have, you know, local minima and things like this. And that's not necessarily a bad thing. Often the minima that you find are actually really quite good. So, like, you know, it's not necessarily bad to have local minima, but it's a possibility, and you might have to kind of consider it when you're, you know, in your algorithm. And often, for example, these having like non-convex losses can mean you're like more data efficient, you find better solutions, etc. So this is not to kind of scare you off of functions like this, but just to kind of point out that there could be some, you know, complications there. One other really remarkable property is that under certain conditions, even if the true thing you want to minimize is this, you can what's called do a convex relaxation and replace a loss like this with a loss like this, and still get the same solution. And we'll actually see kind of a picture of sort of why that might work. It's the same picture in the next page. So convex relaxation is something to know about if you haven't heard of it. It's a very, very cool idea. And okay. Okay, so the case of q equals 1 is known as the Lasso in statistics literature. It's also called like L1 regularization. It has a property that if lambda is sufficiently large, some of the coefficients are driven to 0 exactly. So they're not just shrunk, they actually become 0, leading to a sparse model in which the corresponding basis functions play no role. So yeah, so they'll call this, you know, here L of W is, you know, whatever the error function plus the sum on the absolute values. Right, and this is, you know, you can kind of write this, a fancy way of writing it is as what's called the L1 norm. So you might hear L1 regularization. And it has has a very cool property, which we'll kind of see geometrically in a second, that it will actually send some of the weights to 0, which can be very, very useful. For example, if you're doing kind of like variable selection, you might be interested, like, what variables should I consider? That can kind of give you a good starting point to narrow down your variables in kind of a way that, as I said, doesn't require you to set a threshold. Some values will actually be set identical to 0. Okay, let's see what he's saying here. So this is important. So so to see this, we first note that minimizing. Oh yeah, so let's just back up a bit. So the L1 case has the property that lambda is sufficiently large. Some of the coefficients Wj are driven to 0, leading to a sparse model in which the corresponding basis functions play no role. Okay, so now to see this, we first note that minimizing 3.29, so for any q, is equivalent to minimizing the unregularized sum of squares function subject to the constraint so and so. Okay, so we're going to minimize this subject to our solution living inside this ball. And we'll see a picture of that in a second. For an appropriate value of the parameter eta, where the two approaches can be related using Lagrange multipliers. Then the origin of sparsity can be seen from figure 3.4, which shows the minimum of the error function subject to the constraint. And as lambda is increased, so an increasing number of parameters are driven to 0. Okay, so first let's look at this connection to Lagrange multipliers. Okay, so let's say we've got our, we're trying to see, you know, what is the connection between this and this, okay? And it depends on, you know, okay, so let's just write out. So if we wanted to do this with Lagrange multipliers, we would write out, you know, before we get into Lagrange multipliers, let's just write out the constraint problem. So we say, you know, L of, we want to minimize E of W such that, you know, I'm just going to write this, I'm going to write this as such that is less than or equal to n, okay? Less than or equal to eta. Okay, so what's the first thing we do? Well, so we make a Lagrange multiplier for this. So we go to, you know, and our Lagrangian is now going to be a function of w and this parameter lambda, which is supposed to enforce this constraint. So it's going to be e of w plus lambda times, minus eta. And now the idea is to think that lambda is going to want to try to increase. It's kind of going in the opposite direction. You're trying to minimize. Lambda is going to try to increase, and lambda has to be greater than or equal to 0. And so the idea is that, whenever, if ever this thing becomes greater than eta, this whole term is going to be positive, and then lambda will start increasing, and it will increase and increase and increase until until the constraint is met. So until you arrive at a solution where your minimization satisfies this constraint. Now you can imagine that, so this number here on the left is positive, right? So you can imagine that the more you squish eta down, there will be kind of a course, the lambda, you might need to kind of penalize this lambda that's trying to kind of keep this constraint met. It might have to kind of get larger. Conversely, if you let eta be really large, so essentially not constraining it, then lambda will you can actually almost set it increasing towards 0, and you will still satisfy this constraint. So there's kind of a connection between lambda and eta. So the harder the constraint you're trying to enforce, the larger lambda will tend to get, and vice versa. Okay, so now let's say you've actually found, you found your solution. Let's say someone has told you what the value of lambda is. Then, well, as far as w is concerned, the solution you will find will just be is the one that just minimizes this particular function, right? Because w doesn't show up in eta. So it's almost like you have this kind of regularized function. This is just a function of w. But then kind of lambda is kind of playing this external role, which is trying to enforce the constraint. But if we told you, at the solution, the w that you get will just correspond to some value of lambda. It just depends on what your eta was. And so that's kind of the correspondence, that it just turns out that, instead of thinking about it in terms of eta, you can just think about it in terms of lambda itself. You can say, okay, well, I'm going to set my lambda here, and that will correspond, the solution I find will correspond to some value of eta when I solve this constraint problem. So, this problem here doesn't seem to have any constraints on it, right? It's just like, well, you have w, and there's some lambda floating around. But it turns out that the solution will correspond to a constraint problem for some value of this eta thing that you're trying to keep your weights below. So that's kind of the connection. I hope you kind of get what I'm trying to get at. So although this looks like an unconstrained problem, you're just minimizing w. No one tells you keep it bigger than this, smaller than that. It just so happens that for each value of lambda, you get the same solution as if you did constrain the weights, and the constraint, this value of eta, depends on lambda. So the larger lambda is, the tighter this constraint you're trying to enforce. The smaller lambda is, the larger, the easier it is to kind of satisfy this constraint. Okay, and why do we care about this? Well, it's very cool in its own right, but it also gives us an intuition of why we're getting these sparse solutions. So let's go and have a look. So this is the really crucial picture for understanding, getting intuition for these problems. So, okay, so these are the balls. So we're going. Okay. So what are we looking at here? So these are like this is the called the L squared ball. This is the the L1 ball. So this is equals, and actually they shouldn't be called x's. My mistake. They should be called w's. So this is the sum on wi squared. There's just two w's here, and this is is less than or equal to whatever eta. This is the sum on less than or equal to eta. Okay, and you can imagine as we increase and decrease eta, the ball grows larger and smaller. And now this is our error function as a function of w. Okay, and there's some solution, the unregularized solution. So where there's no regularization, and as we get farther and farther and actually, sorry, this whole thing R, this is E of W, and this is, I'm going to call this W star star. So that's going to be, or let's call it actually W0 because it will correspond to no regularization. And same thing on either side. And so now we have to think about, well, so what is the problem we're solving? It's we're going to try to minimize E of W such that, let's say, sum on Wi to the q is less than or equal to eta. So what does that look like? Well, we have to consider, well, what is this set? So this is where those norm balls come in. So we have to look at, well, what is a set that looks like, and let's consider, for example, let's say for q equals 2, what is a set that looks like, Wi squared is less than or equal to eta? Well, that's just a circle of radius, eta, right? So now what we're trying to do is we're trying to minimize this expectation, sorry, not this expectation, this energy function, this loss, while keeping, while staying inside of this ball. So, and if you just look at the geometry of the situation, well, you can say, well, W naught, the unregularized solution isn't the case. So what we have to do is we have to just keep finding the closest point, because this is because of the shape of the loss, the closest point to W naught that's also inside, or at least touching, this constraint ball. So this is kind of this is coming from the thing we're trying to minimize. This is coming from our regularization. We want to essentially stay as close as possible to W naught while being on or inside this constraint ball. And it turns out, as we have to just kind of keep trying solutions that are farther and farther from from the solution that gives us zero loss, until one of them, the closest one that to W naught that hits this ball. And for when we're minimizing kind of the L, the sum of squared term, well, that constraint ball is actually what we would call a ball. So you kind of hit it at some point where it's W2 is in general non-zero, W1 is general non-zero, it's just kind of somewhere in space. But when the ball is, and so here we're going to have like eta is going to be here. When the ball is the L1 ball, because of its pointiness, the closest point to our optimal solution, so as we're kind of trying to find the closest point we can to our best solution that satisfies the ball, it will almost always be a location where many of the coordinates are actually identically zero. It's because this ball, as you expand it out, the first place it hits, the first kind of valid solution you find, the closest valid solution you find, will tend to be on a point. So you will, unlike in the L2 case where some of the points, you're close to zero, but maybe not quite, here you are actually identically zero, and that's kind of where the sparsity comes from. It also connects to that point I made earlier that, let's say the ball that you cared about was actually like the q equals 0.5 ball, which looks like this. Well, you can see that, here you can still get kind of the same solution, the same sparse solution in this kind of toy example, but without having to deal with all the non-convexity issues. So you can kind of relax the problem to a, this convex constraint while still finding a sparse solution. So that's hopefully gives you an idea of the kind of what the geometry of this problem is and why we get those sparse solutions. So the point is that when it's kind of two steps. When we have a loss like this, we relate it to a constraint problem where we say, look, minimize my error function, but make sure your weights are inside this ball. And then that gives you the intuition. Okay, so it says, okay, I want to stay within as close as I can to this optimal solution, but while being inside one of these norm balls. And if that norm ball is kind of this round, well, you're not going to get a sparse solution. But if it's kind of pokey like that, you will very often get sparse solutions. Another point I wanted to make while we're here is that notice what happens when we make the eta, our constraint, larger, right? So we can kind of make the error bar larger and larger. And eventually, the true solution will actually be inside it. You won't have to move at all. And so that kind of corresponds to the setting of making lambda smaller and smaller. At some point, you eventually don't, the constraint is so loose that it's almost as if the constraint isn't there, and the regularization doesn't matter. If you make the regularization stronger and stronger, that's like making eta smaller and smaller. You end up getting farther and farther from the solution. If the regularization is super strong, well, the only point that survives is 0. So you get shrunk to 0. So I think this picture is really, really important, and you really should have a really good grasp on it to understand what's going on in regularization. But again, I think it's quite a simple idea, and once you get this, I think the whole kind of the types of solutions you get, lots of things will kind of just click together. So I think that's all I wanted to say about this section. I hope it was useful. I hope you learned something. Please let me know if you did, or if you didn't, or if I made a mistake. Happy to fix them as always. And yeah, so hope you enjoyed that, and see you in the next video where we will be talking about multiple outputs. See you then.